We were just rounding for our final answer on page 5 of 8.6, number 3. So 8 followed by 7 turns into a 9. And remember, only when it's money are you allowed to round without being asked. They just assume you know. But any other time, you're never allowed to round unless they ask. So this is money. That's why we're allowed. Excuse me. So our final answer is $22,408.89 because 8 followed by a 7 says turn it to 9. And then always before you go on, I tell students, make sure the answer makes sense. Can 12,000 turn into 22,000 in 9 years? Yeah, that makes sense. So I've had students write 22,256,000 and I'm like, that doesn't make sense. That can't grow that much because it's easy to miss decimal places or maybe type it in wrong or maybe forget the parentheses. So make sure your answer makes sense. So the amount about doubled in 9 years. That makes sense. Okay, so number 4, we're going to have the same, excuse me, type of problem. This one is compounded monthly. So monthly means in. The number of compounding periods is 12. Here's our T. T is 5. 480 invested. So there's my P, 480. And here's my rate. So it's decimal places after the 6. So 2 to the left would make it 0.16. So we are ready to plug and chug. So the amount after 5 years is the principal, 480, times 1 plus R is 0.16 or 0.16 over N, which is 12. Caret, to remind yourself to put that in. And then N times T. N is 12 times T is 5. And we're ready to plug it in. So type it just like you see it. 480 parentheses 1 plus 0.16 divided by 12. Close your parentheses, caret, open your parentheses, 12 times 5, close. So let's make sure everything looks good. We can use our left arrow, 480, 1 plus 0.16 divided by 12, close, caret, open, 12 times 5. Perfect. I always like to look at it first and make sure it's correct. So we have $1,062 and our cents, 2 is followed by a 7, so that makes it 3. So $1,062.63 with the dollar sign. Okay, 1 second. Sorry, I thought something turned on. And let's see if that makes sense. 480 doubled is 960, so it's a little more than doubled in 5 years. That's a pretty high rate of interest rate, so yes, that makes sense. Okay, the next one hopefully will draw your attention here. What's different about this one? Compounded continuously. So that means use the PERT formula from above. So amount after T years is equal to PERT, P-E, and then my exponents RT. And again, it gives you this parenthesis on the calculator after e. It already has the exponent in it, so you don't have to worry about that, but then you have to remember to close that. So this caret will already be built in on the calculator because it's an e. As you saw earlier when we were typing the e's in, second ln, see how it gives its own caret and opens a parenthesis. So we just have to close it. Okay, so we know we're using the continuous compounding formula because we don't know what n is. We don't know how many compounding periods there are when it's continuous. It's infinite. Here's my t, so t is 6. Here's my r. Move it 2 places to the left, so 0.05. And here's my p, 10,000. So let's write the new problem. So the amount after t years is, after 6 years, is principal, 10,000. E, remember, is a constant. You can't replace it with anything. It has its own value. To the r, 0.05 times t, which is 6. So 10,000 e, and then the exponent's going to be r times t, 0.05 times 6. So I'm ready for the calculator again. So 10,000 e, so second ln is where the e is. It gives you the caret, it gives you the opening of the parentheses, so you just type 0.05 times 6 and close it. $13,498.59, because the 8 followed by an 8 says change it to 9. So $13,498. Sorry, I put some white out there because the orange bled through, so it's not writing. So $13,498.59. So before we walk away, let's just make sure it makes sense. So it was 10,000, 6 years later, about 13,500. Yep, that makes sense. So we are good. So like I said, you do not have to memorize those formulas, but we don't give you this on the test. So you do have to memorize these, what these letters represent. So you'll be given 2 formulas. You have to know to use this one when you can count the compounding periods, and this one when you cannot, when it's continuous. And then you have to know what each letter represents. Principal, rate as a decimal, time in years, number of compounding periods. So this part you do have to have memorized, but they will give you the 2 formulas. Okay, let's go to the bottom of the page here. So now we're going to learn about the natural logarithm. So we've learned about e when it's an exponential. Now we're going to learn about e being the base of a log. So when we have a log base e of x, we have a little short notation for it, and that's called natural log of x. That way you don't have to write the e, it's just assumed. So log base e of x is written as the natural log of x, just like we learned in 8.4 that log base 10 of x is just written log of x. Same thing. So we don't write the 10, it's assumed here. We don't write the e, and we write ln. It's actually logarithmia, not the rel. It's a Latin word because we think, why isn't it nl for natural log? Well, it comes from a different language where they say logarithmia, not the rel, something like that. So it's ln instead of nl. But it's just the log with base e. So a log with base 10 is written like this. A log with base e is written like this, and it has its own key on the calculator. So here's our base 10 key, here's our base e key. Any other bases we can't do on the calculator. And that's what we're going to learn at the very end of the section, is how to do like a base 6. We learn the change of base formula, so we can do it. But right now, all you know how to do is base 10 and base E. So let's see what these look like on a graph. So we learned, I'm going to put a piece of blank paper in between so that I don't lead on to the next page. So we learned in 8.4 that the log is the inverse of the exponential. So the exponential, which we just did with the E graph, they had horizontal asymptotes. Well, this is a log, which is the inverse of e to the x, so it's going to have vertical asymptotes, not horizontal asymptotes, because they're inverses, so we switch them around. We do the opposite. These can still be done on the calculator because our calculator does know base E. You should recognize this as the mother function because there's no numbers added, subtracted, multiplied. But this you should recognize as the mother function raised up to. So if I took all the points on this graph that we're going to make shortly and raise them up to, then I would have this graph. So this is the mother function shifted up to, because this is not with the x. If it was with the x, then we'd have parentheses to show that they're together. So this is just a 2 added to the outside, and we learned in chapter 7 that means shifted up to. And you'll see the 2 graphs once we have them made, that one is just the other one shifted up to. So we have to use a little bit of knowledge here. We learned that the argument has to be positive. And we learned this in 8.4 because if you do the log of 0, for instance, it's going to say, nope, don't know how to do it. If you do the log of -5, for instance, it's going to say, nope, don't know how to do it. We only know how to take the logs of positive numbers. That's it. So if they asked you for the domain, which I do ask you for domain on the final exam, and it's good to do it before you graph a problem, it's whatever the argument is must be greater than 0. That's another way of saying a positive number. Greater than 0 means it's going to be a positive number. So that's the mathematical way to state that the argument must be a positive number. We can't do the log of 0 and we can't do the log of a negative, as the calculator will tell you. So why do I need to do that? Why is that important here? Well, it's important because we need to know what to put in for x. So I just remembered something that we forgot to do. Go back to page 4 real fast. We forgot to do domain and range on page 4 because I know I put it on the final. So go to that bottom problem on page 4 and let's do domain and range real fast, because you're going to see that the domain and range get flipped around when we do the logs. So left to right, remember, just like above, we said domain was left to right. It goes left forever. See the arrow? And it also goes right forever. So the domain is -infinity to infinity. Well, we're doing the log graph next, and remember how x and y get flipped when they're inverses? So this is going to be the range of the log graph we're getting ready to do. The range is bottom to top, as we wrote on the one above, and the lowest y is 0, not included. Remember how we can't touch the x-axis, so we need a parenthesis. And the highest y goes up forever, so that's going to be infinity. And that will become the domain of the function we're getting ready to graph now. So this will be the domain, that'll be the range, because they're inverses, we flip x and y. So that's why I wanted to do that one. I just thought, oh, we didn't do that second one. So we'll pick up from